Okay, Maria. So, this atoms chapter we have completed in the last class. Yes.
Yes, ma'am.
Yeah. So nuclei we have to start. So let's start with the class. So basically, this is the last chapter of your modern physics. Then we'll be left with semiconductors. So it's a very short chapter, and most of the things are not included in your syllabus. So those things I'll mention you. Firstly, talking about the nuclei. We in the previous chapter we were talking about the complete structure of an atom. This was the complete structure of an atom. Just a minute. So see, we were talking about the complete structure of an atom. And then see, when you have this atom structures in the central part, we discussed that when Rutherford's postulates were present, we discussed that this is a there is a central part of within the nucleus which is known there's a central part within the atom which is known as the nucleus. Okay, so this is what we were studying. So now nucleus has materials which is known as the nucleons. Now nucleons are made up of the protons and the neutrons. Protons and the neutrons. So when we are talking about the entire structure of an atom, within the central nucleus is present, which is having the nucleons. And collectively, protons and neutrons will be called as the nucleons. Now, what are nucleons? I think you have the PDF already with you and you've printed also them. So whatever things I'll say extra, you can write it and then I'll be discussing the PDF with you. So the nucleons has protons plus neutrons. And when we're talking about the atomic number is basically the number of the protons that are present. Okay. Means this is Z represented by the Z. What is mass number? Represented by A. It's the number of protons and neutrons. Number of protons plus neutrons is the mass number. Now, number of protons is represented by Z. Number of electrons is also the same because number are same. So number of electrons is also Z. Number of nucleons means protons plus neutrons. This is the mass number, that is A. Number of neutrons will be C. Total number of neutrons plus protons is the mass number. Number of protons is Z. So if the number of protons is Z, total number of the nucleons is A. So number of protons plus number of neutrons will be equal to the mass number. So if I want to write what is the number of neutrons, I'll write it as A minus Z. Is it clear?
Yes, ma'am.
Okay. This is just for the number part because, masses will be given, especially in the mass defect, this will be utilized. Now, this is the element which is present. This is how a chemical is represented. So you have on the topmost right part, you have what is the mass number. And on the bottom lower right corner, you have the atomic number. So mass number and you have the atomic number. This is how your element is constituted. Now, this is the chemical symbol. So there are depending upon the variations of Z and A, we have different kinds of substances which you must have studied it in your chemistry already. Like if I talk about the isotopes have the same atomic number, but their mass numbers are different. Like if I talk about the isotopes of hydrogen, protium, deuterium, tritium, all these are present. And you must have studied this in your chemistry also. So see 111, their atomic number is the same because hydrogen holds the first place in the periodic table. So this first position, this will remain as it is. But when we are talking about the mass number, so always remember this side you have here, and one side you have the atomic number. So mass number, when you see this topmost part, this is changing, means you have the isotopes. And when you see this lower part that is present, this is remaining the same. Then this is, you can say these are your isotopes which are present. Nextly, you have isobars. Now in isobars, just the opposite. Means the topmost part that is present, this will be different. And the bottommost part that is present, atomic number, this will be the this will be different, sorry. The atomic mass number will be the same this time. Like in hydrogen, this above was different. That is, the mass numbers were different. Now the mass number will be the same. But when we're talking about the isobars, different atomic numbers will be existing, like chlorine and sulfur. You must have heard about their masses from your periodic table and must have used it in your chemistry also. So 37, 37, this is fixed. But see, sulfur comes just before chlorine, right? So this is how they are isobars. Or you take the example of calcium and argon. See, both of them have different values of atomic number. Argon comes first, then comes your calcium later. But both of them have the same mass. Okay, so these substances, these materials are called isobars. Now, what are isotones? They have the same number of neutrons. And what did I tell you? Number of neutrons is calculated by subtracting the mass number and the atomic number. Like, see, here I'll write 37 minus 17. Here I'll write 39 minus 19. This will be 20. This will be 20. So this is how the isotones have to be written. Next are isomers, and isomers you've studied it in your chemistry already. I think in class 12th you have a proper organic chemistry where you draw the isomers also, right?
Yes, ma'am.
Yeah, so isomers you must be aware. So you know in isomers you never add any carbon compound or you just change its structure. Structures are changed, but they have the different energy states that are present. Those substances are called isomers. So materials are exactly the same. So you have the same mass number, you have the same atomic number present, but the energy states are that are present are different. So isotones, isobars are there, and isotopes are there. Okay, isotopes, isobars, isotones, and isomers. These four things are present. So in your notes, the isomers part is not there. So you can add this line, but first let us go through the notes. Now in the notes, what is a neutron? Neutron is basically a neutral particle that has the mass equal to, almost equal to that mass of the proton. Okay, and it was discovered by Chadwick. So these are the important things only that you need to remember. Coming to the AMU, that is the atomic mass unit, AMU. AMU is basically a conversion unit that is 1 by 12th of the mass of carbon. If you know carbon is written as C12, means 12 grams is the mass for carbon. In your mole concept, you must have used this concept a lot. Especially in the molar concept, this is used. So
Yes, ma'am.
when you're talking about the molar concept, from there you have all the masses. So revise your periodic table once for the atoms and nuclei chapter. So coming to the what is this AMU? Yeah. So 1 AMU is the atomic mass unit. This is 1.66 into 10 to the power minus 27 kg. So if you have this present, just multiply and convert it. Okay. So this is there.
Okay.
A plus Z we have discussed how it is written. A is equal to Z plus N. So the number of neutrons will be equal to A minus Z. Then nucleons are the number of protons and neutrons. So isotopes, isotones, and isobars we have discussed. Here what you can do, here you can just add one line about the isomers that you remember. I'll show you the PDF also. Coming to this relation, E is equal to mc square should be there in your mind. You have the numericals from E is equal to mc square also. Regarding the size of nucleus, let us come back to the class notes. First, you just add this line about the isomers. Just add this line about the isomers. Done, Mariam?
Yes, ma'am.
Okay. Coming to the atomic masses. Now, one thing, Mariam, it's a suggestion that remember the mass of electron, the mass of proton, and the mass of neutron, because it might not be mentioned to you. In some questions, it is mentioned. The question that I'll be showing you, it is mentioned there, but in most of the questions, it is not mentioned. So this is the mass of the hydrogen atom. So mass of the electron, proton, and the nucleus. So these values, if it's better if you can remember. And this is the mass of the hydrogen that I was telling you, 1.0078. Now coming to the nucleus size. When we are talking about the size of a nucleus, so first thing is that the volume of the nucleus. Volume of the nucleus, you have to remember, it is directly proportional to its mass number. This is the whole concept. Mass number. Okay, so basically we can say, what's the volume of a sphere, Mariam? Volume of a sphere?
2 pi r.
2 pi r is the circumference of a circle. Volume of a sphere?
Pi r square.
That is the area of a circle. Sphere, not a circle. Come out of this 2D, 3D. Volume of,
4 by 3 pi r cube.
yes, now you're right. Volume of the nucleus will be 4 by 3 pi r cube. This is directly proportional to the mass number. Mass number is A now. Now, 4 by 3 is a constant, so we can just say r cube is directly proportional to A. From here, I can say r cube is directly proportional to. Now, the proportionality sign can be removed, and this can be equated as is equal to k. Now, the constant term that comes. Now, the constant that here we'll be writing is r naught basically. R naught is actually the constant that comes here into action. So, r naught A, okay? So r cube is directly proportional to r naught A. So I can say, or you can simply say r naught, one step, r cube is directly proportional to A. So we can say that r will be directly proportional to A to the power 1 by 3. Now I'll put the constant. R is equal to r naught A to the power 1 by 3. So this is the whole formula of it. Now what is meant by this? Let us see. So look, R is the radius of the nucleus. This is the radius of the nucleus. R naught is a constant term whose value is 1.2 into 10 to the power minus 15 meters. So this is written as 1.2 Fermi meters also. 1 Fermi meter means 10 to the power minus 15 meters. So according to this conversion, you can remember this 1.2 into 10 to the power minus 15 or 1.2 Fermi meters. If it's mentioned in the question to use the value of R not as something, if it is given to use it like this only, then you put that value, whatever is given in the question. Otherwise, 1.2 is there and that's a constant term. So you should remember it. As it is, it is. Okay, yeah. And what is this A? A is the mass number. So A is the mass number. Hello. So do one thing, Mariam. Just copy this part because this is not there in the notes properly. Just copy this part somewhere and inform me.
Okay.
Okay?
Okay.
You've understood now, Mariam, till here?
Yes, ma'am. Done, ma'am.
Coming to the nuclear density part. So density is always mass by volume. We know this. So when we're talking about the nuclear density, it will be the mass of the nucleus by the volume of the nucleus, because density is mass by volume. So mass of nucleus by volume of the nucleus, that is the density. So let us put the value. What is the mass? See, m is taken as the average mass of a nucleon. Small m. This is taken as the average mass of nucleon. And what is the actual mass of each? We have seen it is a mass number. So multiply the mass with the number, you will get the total mass of the nucleus. Am I right, Mariam?
Yes, ma'am.
Yes. Coming to volume of nucleus. Volume, you have told me it is 4 by 3 pi r cube. So this 3 will be shifted here. 3 ma divided by 4 pi r cube. Now, what is r cube equal to? See, r is equal to r naught a to the power 1 by 3. So, r cube will be equal to r naught a, right? So, if we put it here, this whole terms, whole cube, this will also be cube. So, if I put this value, this will be 3 ma divided by 4 pi r naught cube into a. Now, see, a will be cancelled. Now, if you see all these things, this is a constant term. Mass of nucleon, this is also constant. 4 is a constant term. Pi is also a constant. 3.14, this is a constant term. R naught, we know it's 1.2 fermi-meters. That is also constant. That's it. It means in the density, the nuclear density, this is not depending upon any of the quantities. See, this is not depending upon the mass. If all these quantities are just constant, if you put in the values, you'll always get the same answer. Like if I say, Mariam, calculate the nuclear density for lithium, you will put 3 m pi 4 r naught cube. That's it. So when you have 3 m by 4 pi r naught cube, you do not have anything that will make it different for different elements or different atoms. No. It means this nuclear density, this value will be constant.
Okay.
Now see, okay. Now when you put in the value, the mass, this is 1.66 into 10 to the power minus 27. And A has already been cut into 3 divided by 4 into 3.14 into 1.2 into 10 to the power minus 15 whole cube. If you write this value around 2.96 also is written somewhere, sometimes it is 2.3 also written. So I'll write 2.96 only. So this is 2.96 into 10 to the power 17 kg per meter cube. This is the value that is coming, as it is, this value is coming. Nuclear density is independent of the mass number. Okay, so this is what is it. Okay, for germanium, for silicon, for cobalt, if you take any element, you'll always get this. So remember, nuclear density, however the question tries to trick you, always remember nuclear density is at least going to be fixed if anything is not or not. Okay, nuclear density part also quickly write it.
Okay. Done, ma'am.
Write this question, Mariam.
Okay.
Yes, Mariam. So see, this question says calculate the radius of germanium, and the radius that is the R naught, that is the constant that is given, is 1.1 fermi-meters. Now see, here we are calculating R is equal to R naught A to the power 1 by 3. This is the formula. Now the mass number A is equal to 70. R naught is given as 1.1 fermi-meter. So we are not going to put 1.2. We'll take 1.1. R naught will be 1.1. A will be 70 to the power 1 by 3. Okay. So when you will solve, this will be 1.1 into 4.12 something. So radius will be around 4.53 fermi meters. Okay. Write this question. the solution?
Done, ma'am.
Okay. Coming to the next question, this says express 16 milligrams into mass into equivalent energy. So the simple formula, see, mass is given as 16 milligrams, 10 to the power minus 3 grams. Speed of light is 3 into 10 to the power 8 meter per second. So we are going to use E is equal to mc squared. So here the energy will be 16 into 10 to the power minus 3, 3 into 10 to the power 8 whole square. So the answer will be 144 into 10 to the power 20. No. 16 minus 3, 13. 10 to the power 3, 13. Okay, right.
Done.
Okay, coming to the third question, this says that assuming protons and neutrons have equal masses, calculate how many times the nuclear matter is denser than water. Now see, Mariam, the question is basically saying that the density of nucleus is there, the density of water is there. Now, how much more times is the nucleus denser than water? So whenever you have how many times or whenever you have such comparison questions, straight away keep it in your mind, you have to take the ratio. It is saying nuclear density is present, water's density is also existing. So how will you say that how much times the nuclear density is denser than water? So basically, we know the nuclear density, it is 2.96 into 10 to the power 17 kg per meter cube. Density of water, you tell me, Mariam.
Yes, ma'am.
What is the density of water? Hmm?
1.
1 ग्राम पर सेंटीमीटर क्यूब होता है. एसआई यूनिट में बताओ. In SI unit. 1000. Please remember, Mariam.
Okay.
Okay?
Okay.
1000
Okay.
kg per meter cube. Because density of water is such that will be utilized and you'll need to calculate it in the numerical. So it is better if you will have it with you. Okay.
Okay.
Now, if I take the ratio, so density of the nucleus by the density is 10 to the power 3. So this will be 2.96 into 10 to the power 17 minus 3. That is 4, means 14. So see, you will have so there won't be any unit kg per meter cube will be cancelled. So basically says that nucleus is this much times denser than water. Clear?
Yes, ma'am.
Okay, one last question. You tell me the answer of this, Mariam. It says that nuclear mass of iron is given, that is 55.85 am. It is saying calculate its nuclear density. How should we do this question? Hmm?
Mass by volume.
Okay. See, how many times will I tell you? Nuclear density is independent. Whether I gave you an example also, you have iron, you have cobalt, you have lithium, you have boron, aluminium, anything. Density of nucleus is fixed 2.96 into 10 to the power 14. It is not going to be different. I told you, don't get tricked by such kinds of questions. These questions will be there, which will be giving you different values of volume and mass. Still, the nuclear density will be this. It is independent. Got it?
Yes, ma'am.
Okay, write down this page.
Done. Done, ma'am.
Now, Mariam, second last topic is mass defect from it. So first understand it here, then we'll come to the notes part also. Now, the total mass of protons, see, number of protons is Z and mass of each proton is MP. So total mass of protons will be number multiplied to each's mass, that is ZMP. Fine?
Yes, ma'am.
Okay. Similarly, the number of neutrons is A minus Z and number of each neutron is, mass of each neutron is MNU. I have written so. And total mass of nucleus is this, or M capital N, I write. Now, what we do in order to calculate the mass defect is basically, see, the actual mass of the nucleus that is present is the total mass of the nucleus. Plus, because of the transfer, whatever is the change in mass coming, that difference is the mass defect. Suppose I have this whole thing and I have this. I want to find out the change. This will be the change. So what we do, we first see what is the mass of the nucleons that are present. Means ZMP, that is the mass of protons, plus A minus Z Mn, that is the mass of neutrons. This will give me the total mass. I'll subtract this from the mass of the nucleus. So I'll get whatever is the change, that is the mass. That is written in this formula. It is saying ZMP plus, it is saying ZMP plus A minus Z Mn, right? A minus Z Mn minus Mn. This is what is written as the mass defect. So ZMP is the mass of the protons plus A minus Z is the mass of the neutrons. So you have added the mass of the protons and you've added the mass with the mass of the neutrons. And then you've subtracted it with the mass of the nucleus. This is what is the mass defect. Delta
Okay.
M is the mass defect. This is how you have to calculate. I'll make you see a question also. Now, there is a concept of binding energy. What is this binding energy about? Binding energy basically, see, if elements are held within the nucleus with some energy, okay, that is binding all the materials intact. So what happens if this breaks into segment? The energy that was earlier binding the materials gets released into the system. So this is known as the binding energy. Okay. So how to calculate binding energy? Take the square of speed of light. Okay. That is c square. And calculate the mass defect. Then multiply whatever is the mass defect with this speed of light square. This is the binding energy. Now, see, if I multiply this whole formula with c square, I'll get binding energy. Now, what if I want it for each and every nucleon? So I'll say binding energy per nucleon. Now, there's a formula for it. Instead of calculate, see, when you will multiply it with c square, that is the square of speed of light, you'll get the answer in joules. If you multiply it with 931, you'll get the answer in mega electrons. So usually you can leave your answer in electron volt also, right? Electron volt is a standardized unit. You can leave your answers there. So delta M into 931 is also used as the unit. Now, if I want to say binding energy per nucleon here, so I'll take mass defect into 931 mega electron volt and I'll divide it by the mass number. Remember this? This is the binding energy per nucleon. I'll repeat this in the notes. Wait. Let's come to the notes. So E is equal to mc square, size of nucleus. R is equal to R naught, a to the power 1 by 3. Density also, that it is fixed 2.97 into 10 to the power 17 kg per meter cube. This is fixed. So density of nuclei of all atoms is same. Remember, in the questions like those questions of iron, you will be getting the same value. So do not just worry about it, that whether it's any element is present or not. Straight away, just keep on writing the value of density as 2.96 into 10 to the power 17. Fine.
Okay.
Okay. The force between nucleons. See, in your class 11th, you must have done this gravitational force. F is equal to gm1 m2 by r square. Remember, Mariam? You must have done it. Yeah. So if we say two protons are mentioned and between two protons, we are calculating the gravitational force. So that is this value. And when we are using the Coulomb's law and calculating the value, so when you take the ratio, we get 10 to the power 36. So since your Coulomb's force is there in your syllabus, that's why a discussion is there made here. So electric force is 10 to the power 36 times the gravitation. Okay? Now, what are the properties of nuclear force? So see, the nuclear force is 10 to the power 38 times stronger than the gravitational forces. Short range forces are there. Nuclear forces are basically strong attractive forces up to a distance of 1.5 fermimeters. But at a distance of, just a second, please just wait. Yeah. Okay. So nuclear forces are short range forces and they are, see what happens is the potential energy is the maximum positive here. Now it decreases, it reaches zero. See, it touches this graph, it reaches zero. Then it further becomes negative, and negative for potential energy is very good. Like negative value of potential energy is considered very, very good because it is the most attractive. And when it is attractive, it keeps your system bounded. Bounded system means a stable system. So you will always want a negative potential energy. Now, this says that nuclear forces are basically strong forces up to distance 1.5 fermimeters. But at a distance of 0.8 fermimeters, it changes to repulsive forces. Then it is saying nuclear forces are charge independent. Okay. Now, nuclear forces are spin dependent. If you have studied the electronic spin in your chemistry, there you had this part minus half and plus half for a system. So it is like that. And they are non-central forces. Non-central forces means like Coulomb's law, Coulombic force, electrostatic forces. Those are central forces. When you join the two charges, there's a central line which is running through it. So if the Coulomb's law is existing, it will act on a line joining the centers. That's why they are called central forces. Nuclear forces, nothing is like that, that they have to join the centers. Regarding this graph, so at a distance of 0.8 fermimeters, it reaches the maximum negative value of the potential energy. So this is what is written in the graph. See, potential energy is minimum at a distance R naught of about 0.8 fermimeters. This means that force is attractive for distance larger than 0.8 fermimeters and repulsive if they are separated by distance less than 0.8 fermimeters. Then what's a nucleon? Proton and neutrons are collectively known as the nucleons. Now, when we're talking about the mass defect and the binding energy, we have seen its formula. ZMP plus A minus ZMN minus Mn. This is just showing the mass of the nucleus, entire nucleus. Coming to binding energy graph. Okay, now binding energy graph is there in your syllabus and it is very important. Yeah, so this is the mass defects formula. What is the mass defect? See, difference between the sum of the masses nucleons constituting a nucleus and the rest mass. This is the mass defect. Now, we discussed this. Coming to binding energy. So when nucleus is formed from the free nucleons, the decrease in mass of the nucleons is released as equivalent energy. The energy equivalent to mass defect is used in binding the nuclear and is called the binding energy of the nucleus. In order to break the nucleus or to completely separate the nucleus from each other, an equal amount of work has to be done. The binding energy of nucleus may be defined as the energy equivalent to the mass defect or the nucleus. So binding energy is basically delta m c square. This is the formula of binding energy. This we saw, and I think, is it clear till here, Mariam?
Yes, ma'am.
Hmm? Yes? No?
Yes, ma'am.
Okay.
Clear, ma'am. Understood.
Mariam, this is the last topic of this chapter. You don't have to do anything apart from this topic. Means do not study anything from page number 7. Page number 6 is the last. Alpha decay, beta decay, radioactivity. Nothing is included in the syllabus. Okay.
Okay, ma'am.
Coming to this graph, see this binding energy graph. This is plotted for various atoms. Okay. And this wasn't observed very smooth. This graph wasn't just observed very smooth. So, see, for hydrogen it is there, then it sinks down. Then there are various kinks observed, and then this is the graph that is plotted. This is how the graph is plotted. Now, it says that what there are two main points that you have to remember. See, for the elements which have the mass number less than 30 till here, 18, 12, 18, 14, 4, like these, all these elements, and above 170, like these, 184, 197, 238, these. Between these two, see, these are all less than 31s. These are all more than 170. Almost a constant kind of slope is observed. Not a perfect constant graph, but a little bit more equivalent graph is obtained. But apart from it, that is the first point you have to remember. Second is that you can see energy is low for this group and this group also. See, the main features of the plots. Look at these 2 points. Binding energy per nucleon is practically constant. That is independent of atomic number for nuclei of middle mass number, that is less than 30, more than 70. The curve has maximum, yeah, this one point I forgot to tell you. If you noticed, for the iron Fe56, it has the maximum value, that is the peak of the graph, you can say, is obtained at this point. So what all conclusions we can say about the graph? Binding energy per nucleon is practically constant, that is independent of atomic number for nuclei of middle mass number. These are the two conclusions. Coming to the conclusions from these two observations. So force is attractive and sufficiently strong to produce binding energy of few mega electron nucleon. Short range force, heavy nucleus have lower binding energy as compared to the one in which are having between 70 to 120. Then consider two very light nuclei joining to form a heavier nucleus. Binding energy per nucleon of the fused heavier nuclei is more than binding energy per nucleon of the lighter nuclei. This means that final system is more lightly bound than initial system. Again, energy would be released in such a process of fusion. This means that the energy that is holding all the materials inside the nucleon, inside the nucleus, when the binding energy is released, all these will be uh, released out. This is what is the binding energy curve. So just draw the curve if it comes in the exam and write down the main features and then the conclusions from the above. That's it, what you have to remember from this. Okay, Mariam.
Okay, ma'am.
But let's come to this questions from here. Do one thing. First, write this question. Roughly give 5 minutes and try this question. In 5 minutes, I'll discuss this. But at least just try. This is the last question from the nucleus chapter. Okay?
Okay, ma'am.
While I'll share the semiconductors notes also with you. Okay?
Okay, ma'am.
Mariam, did you get the semiconductors notes?
Yes, ma'am.
See, here, Mariam, shall we discuss? See, here the mass of the neutron, the mass of the proton, and the mass of the entire nucleus is mentioned. And calcium is
Okay.
there with its mass number and the atomic number. So what we do, the first step is we calculate ZMP. So Z is the number of the protons, that is the atomic number 20, into mass of proton, it is 1.00782. So this is equal to 20.1565. Okay. Now coming to mass of neutrons. So that is A minus ZMN. A minus Z is 40 minus 20. So this is 20 into 1.008665. So this is equal to 20.1733. Now, what did I tell you the first step? Add these two. Okay. When you will add these two, it will be 8923.04. This is it when you are adding it. Okay, so what have we done? We have basically added ZMP plus A minus ZMN. That part we have done. And then you are going to subtract it with the mass of the calcium. That is the complete mass of the nucleus. So it is 39.962589. When you will solve this, answer, the delta M will be 0.367. So see, first we did ZMP, then we did A minus Z Mn, and we added these two. We got the whole part, and then we subtracted it with the mass of the nucleus. Tell me, is it clear how have we got the mass defect? Clear, Mariam?
Yes,
Or
ma'am.
should I repeat? Yes, Mariam, is it clear or should I repeat?
Ma'am, it's clear.
Okay, but we have to find out binding energy per nucleon. So binding energy, the change in mass is 0.367 into 931 mega electron volt. This is how we calculate. Per nucleon is this, so we'll divide it by 40. So answer will come around 8.541925. Okay, please write this too.
Okay. Then, ma'am. Then, ma'am.
Okay, Mariam. So one chapter we are left with is semiconductors. This is the last chapter that will be left. So I have shared the notes with you. Let me just start with it, the basic parts. Then tomorrow I'll continue with the notes properly. Basically, what are the semiconductors? So we've studied about the conductors, we've studied about insulators, conductors and insulators, and this entire chapter will be linked with your current electricity, which we have studied in the first book, chapter 3. So that time, uh, I think we have not done, no? We have started with ray optics. Yeah, R is left. We'll be discussing it. So in current electricity in school or somewhere, you must have studied it. So basically, like semiconductors have the properties in between of the conductor and an insulator. Like the conductors have low value of resistivity. Insulators have high values of resistivity. Semiconductor will be having lesser than insulator, but more than conductors, means in between the two. Similarly, conductors have higher value of conductivity. Insulators have low conductivity. So semiconductors will be having intermediate conductivity between the two. This is not mentioned in the notes. Write this also. Just make the chapter semiconductors, write classification of solids, and make the headings about conductor, semiconductor, and insulator. This is not mentioned in the notes. Okay.
Okay, ma'am. Done, ma'am.
Okay, Mariam. So we'll complete this tomorrow then, semiconductors. All right. So get the notes of semiconductors also printed, 13 pages.